make more precise the way that we think about uncertainty, the way that we reason under uncertainty. When we know that people are so bad at reasoning under uncertainty, then probability theory is the right tool to do it. And this idea was first, in some ways, almost as old as probability theory itself, but it was first sort of fully set out by Emile Borel, who also came up with the image of infinite numbers of monkeys at typewriters, and by responding to the work of the economist John Maynard Keynes. It's bolstered in particular by a theory called Cox's theorem. And Cox's theorem says, okay, you're not sure that probability is the right tool, so you can come up with your own way of mapping your intuitive sense of likelihood into numbers. You can come up with your own numeric scale, or for talking about likelihood. Are you sure?
Yeah, they only have to be comparable. They have to form a linear order.
I thought it. Anyway, we've read different papers about this clearly. And suppose then what Cox proved was that if your system meets certain reasonable assumptions, then it will essentially be equivalent to probability theory. So if your system has properties such as that if you tell me the probability, if you tell me your likelihood, whatever number you give me, that Germany will qualify this afternoon, then from that I should be able to work out your likelihood that Germany will not qualify this afternoon. That we should be able to work out the likelihood given the opposite.
That's what the first line means, is it?
That's what the first line means, expressed in mathematical language.
Which is with or without goal line technology.
The second example covers that kind of thing, actually. So supposing we say that we have a probability that Müller will score a goal during this match, and we have a probability that, or a likelihood, a sense of likelihood, whatever way, that if Müller scores a goal, then Germany will qualify. Then we say, well, your system should be able to put those two things together, and from that give us a likelihood that Müller will score a goal and Germany will qualify, to conjoin the two. And Cox comes up with a few rules like this. Some of them are a little bit more technical than that, but they're all reasonable assumptions to make about how we might think about likelihood. And Cox was able to show that if our system meets these reasonable seeming rules, it is essentially probability theory. That you might move the numbers about a bit, but it will be exactly isomorphic to the probability theory you already know. And that gives us a strong argument to think that the only language that can talk about our subjective sense of uncertainty about something like this afternoon's match in a precise way is the language of probability theory. Yes, right. So I can only give one example of the sorts of mathematics of reason that I've been talking about, and so I'm just going to give a brief introduction to Bayes' theorem, which many of you may have heard of, but is always easy to lose track of. And so it's a simple example. We suppose that 20% of the population have this disease, and so you think, oh, I've got 20% chance of having this disease, and then we take your blood and we do the test, and the test is very inaccurate. It's only 80% accurate because that makes the numbers a lot easier. So it's if you've got the disease, you've got an 80% chance of a positive result. If you don't have the disease, you've got an 80% chance of a negative result. So you do the test, you get a positive result. Now you've got that result, what are the chances that you have the disease? Bayes' theorem to the rescue. This is exactly what Bayes' theorem tells us. So here's 100 people. 20% of them here have the disease. 80% of them here don't have the disease. So we give them all the test. The ones who have the disease, 80% of them here get a positive result. The ones who don't have the disease, 80% get a negative result, and 20% of them get a positive result. So now you've had the test, and you know you've got a positive result. Then what that tells you is you're somewhere in this L-shaped region here. And that's all that you know. So you can calculate the area of these two regions, and you find that both of them are 16% of the graph. You can actually just count the squares. And all you know is that you're somewhere in this L-shaped region. You could be anywhere in it. So your chances of being in this half rather than this half are 50-50. You add these two together, 16 plus 16 is 32. This is 16 of those 32. So divide one by the other, you've got a 50-50 chance of being inside this block. And the significance of this is that this is a mathematical formulation of how we change our minds in response to evidence. We start off thinking we have a 20% chance of having the disease. We gain this new evidence that we can quantify in this way, and that moves our probability, our perception of the probability, from the 20% mark started at to the 50% mark. And most people's guesses at where it should move are much further. They use the likelihood of the test as an anchor. Most people's guesses are much closer to 80%. But you can see from this diagram that because the disease is so rare, that and because the test is so unreliable, that it actually only moves you to the 50% mark. Are there any questions about this before I move on? Brilliant.
I'm just curious about how many people are able to calculate it correctly, because before you showed that graph, I thought it's about 50% if you get a positive result.
Yeah.
I was wondering how many people.
I don't know. I don't know if that's. I mean, I know that most doctors can't. You should bear in mind that when your doctor gives you information about tests, you're better off doing the math yourself than letting your doctor do it, because they suffer from exactly the same problem. It's called the base rate fallacy. Once you've got the evidence, you throw away the fact that 80% of people don't have the disease. You don't integrate that at all. You just say, oh, it's 80% reliable, so it must be about an 80% chance I have the disease.
That's another one where the false positive is a better mistake to make. Because if you think you've got disease and you haven't, you'll go and get the treatment, and you're still wrong.
But people show a base rate fallacy in whether or not a false positive is what you want. And people show,
I wonder if you changed the statistics so that you were slightly more likely to not have the disease. Made the test slightly more accurate, so.
I don't know.
Sorry, slightly less accurate. You have to make it.
I don't know. I would be interested to see the research, but I don't have it in mind, I'm afraid. I'm sure that these sorts of experiments have been done, because they've done quite a lot of experiments on the way that people practically update on evidence and the way that people treat these sorts of statistical information. But I don't have it to hand, I'm afraid.
So people predict that they're more likely to have the disease than they really are.
Yes.
So that's a bias towards making a false positive prediction, isn't it?
That's true, but
is that general or not?
I don't know.
Okay.
I'm afraid I don't know. I would guess that there probably is some effect there, but I would guess also that people neglect the base rate even when it's the other way around. In fact, I'm pretty sure they do. So again, I can only cover this one technique, which is a fairly swift one. There's a whole load of other techniques that are worth knowing about. So Solomon-off induction is use the what's called algorithmic information theory, which is the question of how short a computer program does it take to what's the shortest computer program that produces this result? You can produce a pi with a very short computer program, but if you want to print the Encyclopedia Britannica, there's a limit to how far down you can compress that. And so Solomon-off induction takes that and turns it into a form of Occam's razor. It says it prefers a simpler explanation in a mathematically very precise way that tells you where you might start from before you start integrating on the evidence available to you. Von Neumann-Morgenstern utility theorem, which is very relevant to dealing with the bias of scope insensitivity, which sets out a very strong argument that the only way you can be rational about moral choices is to effectively decide an exchange rate. If you can't work out whether to save 100 kittens or 10 babies, then you have to work out what the exchange rate is between kittens and babies. And if you apply a consistent exchange rate, you'll make consistent moral decisions. Very few people do this. The von Neumann-Morgenstern utility theorem shows that it's very, very hard to argue that a morality based on the consequences of your actions can be consistent unless it is integrated over probabilities and if it appropriately weights things by their likelihood and by a sort of single exchange rate for value. The whole field of economics is in many ways to do with these sorts of measures of what rational behaviour is. The sort of notion of the rational actor that much of this comes from springs from economics. And game theory also, which arose in many ways from trying to understand nuclear conflict, analyses the way that we take decisions in the presence of other people who are trying to think about how we take decisions when they take decisions. Or pico-economics, which is one that particularly fascinates me, which tries to understand the certain aspects of human behaviour by treating us as an ensemble of actors who all have different interests. Actors who maybe are thinking of what we want now or tomorrow, and other actors who are thinking of longer, and model the conflicts between these actors using the